From lecture 1 to 3, we already discussed different types of flip-flop, D, T, SR, and JK flip-flop, and its truth table and excitation table. And after that, in lecture 2, we already discussed how to design a synchronous counter by using a D flip-flop. Okay, so first watch lecture 2, how we can design a flip-flop. Sorry, how we can design a counter using D flip-flop. After that, you can watch this lecture 4. Okay, so in lecture 4, we will use other flip-flops to implement the up counter and down counter. We will also discuss one special counter is known as a decade counter. And first, we can discuss one question. We need to design a 2-bit up counter by using JK flip-flop. So in order to implement up counter, and very specifically, we are discussing synchronous type counters. We already discussed what do you mean by synchronous and asynchronous counter. Now we are going to discuss about 2-bit up counter using JK flip. So this is the design step, state diagram we required. So up counter means we know that initial state of the flip flop is 0 0. So for 2-bit we required actually 2 flip flops. So we can consider 2 JK flip flops. This is J and K, and we also required a clock signal. So let it be the clock signal, and output Q and Q bar. Similarly, we require 2 flip flops. So we can consider other flip flops, which is J, K, and there is a clock signal, and you can also consider Q and Q bar. So we require 2, so we can indicate Q1, J1, K1, Q1, Q1 bar, J0, K0, Q0, Q0 bar. Okay. So the states indicating Q1 and Q0. So when it is 0 0, and when you apply clock signal, it's an up counter, next state will be 0 1. Okay, and again if you apply clock, it becomes 1 0, and again if you apply clock signal, the state goes to another state, that is 1 1. So we got all the sequence 0 0 0 1 1 0 and 1 1, and again if you are applying one more clock, it goes to 0 0. So this is the counting sequence of the flip flop. So the present state, you can write the 4 status like this. If it is 0 0, okay, and 0 1, and okay, you can start from. So if it is 0 0, and another one is 0 1, and next option is 1 0 and 1 1. Okay, assume that the present state you can expect 4 conditions: 0 0 0 1 1 0 1 1. And if it is 0 0, then this is a state called Qn, and this is a state called Qn plus 1. Okay, for each one Q1 and Q0. So if it is 0 0, the next state should be 0 1. So from the state diagram we can write 0 1. If it is 0 1, the next state should be 1 0. And if it is 1 0, the next state should be 1 1. If it is 1 1, the next state should be 0 0. So you can fill the present state and next state. Now we need to consider the excitation table of JK flip flop, because we want to implement by using JK flip flop. We know that there is a transition of Q1 from 0 to 0. Okay, so in order to occur, this actually indicating Q1, this is also Q1, and this is also Q0, but in the next state. And Q1 you can expect a change from 0 to 0. When there is a change from 0 to 0, your JK input should be 0x. So you can write it should be 0x. So J1, K1. And next one, Q1 is 0 to 1. 0 to 1 means the JK input should be 1x. Okay, 1 and on. Next one is 1 1. If it is 1 1, it should be x0. Okay. Then again, if it is 1 0, it should be x1. So we got the table of J1 and K1, or we can say the different input combination of to get this Q1 transition. Now we need to think about the other transition, that is from Q0 transition. So Q0 is changing from 0 to 1, And if Q0 is changing from 0 to 1 means 0 to 1 this possibility, so it should be 1x. So 1x you can put. And again this 1 is changing to 0. If this changing 1 to 0 means it should be x1. Okay. Again, if Q0 is changing from 0 to 1, 0 to 1 means again you need to put 1x. Okay. Again this 1 is changing to 0. So 1 is changing to 0 means again x1. So we are getting like this 1x x1 1x x1. Okay. So we identified different types of inputs that require to get this kind of transition. So we got a state diagram, we got the truth table. Now we need to implement the Boolean expression. So in order to implement the Boolean expression, we require J1. Okay. So four values we need to design. Okay. First we can design J1. J1 in terms of the present state. Okay. So we can write present state. Don't get confused with next state. So present state is the available one. So J1 we can design by using Q1 and Q0. So it's a two variable K map, okay, 0 1 0 1, and you can assume that J1 values, if Q1 Q0 is 0 0, it is 0. Okay. And for 0 1, okay, for 0 1 it is 1. Okay. Here it is 1, and other values don't care. Okay. So J1 you can identify from this particular table and you can indicate here. Now we can see that we can group this like 1 and don't care condition. So the corresponding value of this group, you can write J1 is equal to Q0. Okay, this is Q0. Now similarly you can design K1 from the table. We need to design K1. So K1 is here, and for corresponding values of present state, so Q1 and Q0. K0 1 0 1. So you can see that K1 is x x 0 1. Okay, so again you are getting the same thing. K1 should be equal to Q0. Now we need to design J2, sorry, J0. Okay, J0 we can design. This is J0. Again, in terms of present state values, Q1 and Q0. Okay, don't get confused. You never take next state. You need to design by using present state. So J0 values are 1x, 1x. So you can consider all these as a single group. So it becomes 1. So J0 should be equal to 1. And now we need to design K0. If we take K0, again Q1, Q0, this is K0. K0 values, if you are indicating 1, sorry, don't care, 1, don't care, 1. Again, you can group all these values. So of all these values are means it's 1. Okay. So K0 is also equal to 1. So now we got the Boolean expression. Now we need to implement the circuit. So we already identified that we require two flip-flops. So now we need to make the connection. So J1 should be equal to Q0. So J1 should be equal to Q0. So there is a connection between Q0 and J1, and K1 should be equal to Q0. So the same Q0 should be connected to K1 also. So Q0 is connected to both J1 and K1. Now J0 and K0 should be connected to 1. So we can short these two values, J0 and K0, and should be connected to 1. Okay. Now we need to connect the synchronous circuit. We are discussing about a synchronous. So we need to connect the same clock for both flip-flop. Okay, this is the clock signal, and the Q1 signal, and this is the Q0 signal. So this is Q1 and this is Q0. So you will get 0 0 0 1 1 1 in this particular pins, Q1 and Q0. So this is the design part of the 2-bit up counter. Now we can discuss the waveform also. So this is a circuit. The only thing we are just reversing the order. Okay, so don't get confused. The two diagrams are exactly same. Okay, in this case, first J0 is run and second one is J1. Okay, that's only difference. Here you can see the Q0 is directly connected to J1 and K1. Okay. But when you verify the output, this is Q1 and this is Q0. That's the only difference. Okay. So now we can verify the output. So this is a positive edge triggered clock. Okay. So we know that this is a Q0 output. For first rising edge, we can verify the Q0. Okay. So this is actually 0 0 initially, this is 1 0, and this is 0 1, and this is 1 1, again it's 0 0. So you can see that Q1 Q0, if you consider Q1 Q0 in this particular manner, the first value is 0 0. Okay, after that it becomes 1 0, sorry, 0 1. So Q1 is first, then it is 1 0, then finally it is 1 1. Okay, it will operate. After that, again go back to state 0 0. Okay, this particular circuit will operate as a 2-bit up counter. Now we'll discuss a 3-bit down counter using a T flip-flop. So for that, we required actually the state. So 3-bit means you need 3 flip-flops actually. So we can see that down counter, it is 1 1 1. So from 1 1 1, if you apply clock, it will go to the next state. That is 1 1 0. Okay, from 1 1 0, you can expect a next state which is equal to 1 0 1, which is equal to 5. Then again, if you apply clock, it will go to the next state. It's 1 0 0, and again, if you apply clock, it will go to the next state. It's 0 1 1, and again, if you are applying a clock, you can expect this particular state is 2, and again, if you are applying a clock, 0 0 1. After that, go to the state 0 0 0, and again, if you are applying a clock, it will again go back to the 1 1 1. Okay. So it's 7 6 5 4 3 2 1 0. Okay. Now we go to the state diagram. So you can write here we required actually 3 flip flops. Okay. The first one, and the second one, and the third one. Okay. And it is indicated as here we are using T flip flops, so we can indicate TA, TB, and TC. Either you can write T3, T2, T1, or you can write TA, TB. So this is QA, this is QB, and this is QC. So here the variables are QA, QB, and QC. Either you can write Q3, Q2, Q1, or QA, QB, QC. So here also we require clock. Okay. So QA bar, QB bar, and QC bar, because we required 3 flip flops, so that 3 flip flops are labeled as A, B, C. That's all. Or you can write 3, 2, 1. And now we can construct this particular excitation table. So in order to write the excitation table of a truth table of this particular circuit, it's actually excitation table. So we required the excitation table of T flip flop. So now we can see that present state and next state are indicated. So 3 variable. So QA, QB, QC. So this is the present state, and we can call it as this is Qn, and this is Qn plus 1. Okay. Now we can see that even if it is a down counter, when you write the present state, please write in the sequential order. Okay. We know that it's a down counter, but when you write the present state conditions, you write 0 0 0, 0 0 1, 0 0 1 0, 1 1, up to 1 1 1. So okay, in the sequential order itself. Okay. And once you get the 0 0 state, what will be the next state? So from the state diagram, we know that if it is 0 0 0, the next state is 1 1 1. Okay. So this we can obtain from this particular state diagram. And if the stage is 0 0 1, okay, 0 0 1, next state is 0 0 0. Okay. From the state diagram. If it is 0 1 0, 0 1 0 is here, and next state is 001. And if it is 003, sorry, 00011, that is 3 actually, next state will be 2. If the state is 4, next state will be 3. If present state is 5, next state will be 4, okay, from the state diagram. If the present state is 6, next state will be 5. If the present state is 7, next state will be 6. So we got the present state and next state. Now we need to identify what should be the input of the T flip to obtain such kind of input. So for example, QA is changing from 0 to 1. So it's a toggle flip-flop. We are using T flip-flop. Okay, so this is T flip-flop excitation table. 0 to 1 means there's a change. So we know that TA, if there is a change from 0 to 1, the T input should be 1. So you can write 1 here. Similarly, you can complete 0, 0 means it's 0. If it's 0, 0, it's 0. Similarly, if it is 0, 0, again it's 0. And when there is a change, there will be 1. Okay, here you can expect a 1. In all other cases, the state changes are same, so 1 to 1. So all these values are 0. Okay, now we can complete TA. Similarly, you need to consider TB. Okay, we need to write TB also. Okay, you need to write TB. You need to observe the changes in QB. So this is a change in QB. So it's changing from 0 to 1. So TB equal to 1. Here it is from 0 to 0. So it's 0. In the similar way, you can complete the remaining. And now we can think about QC. So QC is changing from 0 to 1. So it is 1. Again, QC is changing from 1 to 0. Again, it's 1. So by observing the excitation table, you can complete this table also. Okay. So now we can complete this table. Once you get the particular table, you can draw the circuit diagram. So to implement the circuit diagram, you need to design the Boolean expression. So Boolean expression for TA. So TA in terms of QA, QB, QC. So we need an 8 variable K map. So not the 3 variable K map. So there will be 8 columns. So QA, QB, and QC. So if you observe, there will be 1, 1 in 2 cases. That is 0, 1, 2, 3, 4, 5, 6, 7. In cases 0 and 4. So this is 0 and this is 4. And all other cases, it is 0. So you will get something like this. You can group these two values. You will get QB, QC. So your TA is equal to QB, QC. Now, now we can design the next case. Sorry, it's QB bar and QC bar. This is 0, 0 actually. Okay. So QB bar, QC. Now we need to design TB. To design TB, you know that the one cases are 0, 2, 4, 6. So again, we need a K map. T 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. This is 0, 1, 2, 3, 4, 5, 6, and 7. So we know that here it is 1, and here it is 0. Again, it is 1, 3, 0. 4 is equal to 1. Here it is 0. Here it is 0, and finally 6 is equal to 1. Okay. So we can make a group of 4 here. So based on this, TB can be written as this is QA, QB, and QC. So in the first and last column, QC bar. So we got TB, TC. Now we need to design TC also. So QA, QB and QC. So if you write, you can see all values are 1. So 1, 1, 1, 1, 1, 1, 1. So you can make a group of 8, so which is equal to 1. Means your TC should be equal to 1. So we got the Boolean expression. Now we need to implement this particular circuit. So for the implementation, we required 3 T flip-flops. This is TA, and this is TB, and this is TC, and the clock signal also. So we need to connect clock. This is QA, and this is QB, and finally QC. Okay, this is QA bar, this is QB bar, and this is QC bar. Now we can check each circuit. TA should be equal to, so I think TA is designed like this. So TA is designed QB bar and QC bar. So it should be connected to an AND gate. Okay, so this is an AND gate output, QB bar. So QB bar we can obtain from this particular point, and this is not QB, it's actually QB bar. This is QB bar, and this is QC bar. So you'll get QB bar and QC bar. Now TB is equal to QC bar. So this is the next equation, TB. TB is equal to QC bar. So QC bar is already available at this particular point. So you can connect here. You can redraw this again. This is QB bar, and now we need required QC bar. So this is QC bar is connected here. Now TC is equal to 1. So TC should be connected to 1. Okay. Now synchronous clock. So all clocks should be connected to the same point. Okay. This is a clock signal. All these counters are synchronous counter. Now we are discussing synchronous count. And you can see that the output values here. This is QA will be one output line. QB will be other output line. This is QC. QA, QB, QC. Okay, 3 output lines. QA, QB, and QC. So you can observe the output of a down counter. Now we can discuss one more circuit that is known as a BCD counter. BCD counter means that BCD number is from 0 to 9. After this 9, 10, 11, 12, etc. are invalid in the case of BCD, only 0 to 9. So 4-bit we are required. So a 4-bit counter we need to design. So you can see the state diagram here, 0, 0, 0, 0, 0, 1, 0, 0, etc. When it reaches 9, again it should go back to 0, 0. But when you write a 4-bit value 0, 0, 0, maximum it reaches 1, 0, 0, 1. And again, if it is a 4-bit up counter, it goes to 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. But when it reaches this particular stage, again it should go back to the previous state. Not the previous state, it should go back to the 0, 0 state. So these states are don't care conditions in the case of BCD. Now we can write the table here. So by using again we can design by using T flip-flop. You can use any flip-flop. Now we can discuss design by using a T flip-flop. So here you can see the present state is 0, 0, 0. Okay, from 0, 0, 0, the next state is 0, 0, 1. From 0, 0, 1, okay, it is 0, 0, 1. Next we are going to 0, 0, 1, 0. That is 2. Okay, similarly we are can go up to 9. From 9 it will go to the 0, 0, 0. When it is 9, again it go back to the state called 0, 0, 0, 0. Okay, this is the counter design. And in order to get this particular state, we need one more circuit. That is, when it reaches 9, you need to reset the counting cycle. Okay, So again, the counter output should be equal to 0, 0, 0. So for that, we need to design a special circuit also. When it reaches 9, it should be identified. So for that, we are using an extra output line. This is known as output Y. Okay, this is Y output. It will be 1 only when it reaches this particular state, 0, 1, 0, 0, 1. Now, if it is a T flip-flop, we can develop this excitation table by observing the normal excitation table of a T flip-flop. Now we can say Q3 is changing from 0 to 0. So your T3 should be equal to 1, 0. So if it is 0, 0, T input should be 0. Next, similarly, you can complete T3 values. When Q3 is changing from 0 to 1, the T3 value is 1. In all other cases, same. So again, you can see that's 1, 1. 1, 1 means T input should be 0. And the similar way, you can design each one, Q2, Q2 change you can observe, and you can fill this T2 row, sorry, T2 column. Q1 changes you can observe, and you can fill T1, and Q0, Q0 you can observe, and you can fill T0. Okay. After completing this, you can move to the Boolean expression part. Okay, in the Boolean expression part, we need to design T3. So T3 by using Q3, Q2, Q1, Q0. Okay. So for that, I can design this. You can consider okay. T3 we can think about that 0, 1. Sorry, we need one more. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if you design T3 in terms of Q3, Q2, Q1, and Q0, okay. So you can see that T3 is equal to 1 only in two cases. It is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is 1 in 7 and 9. So is equal to 7 and 9 is here. So two possibilities. So and the other cases which we discussed from 10, 11, 12, etc. you need to consider as a don't care conditions. Okay. So you can write that values here. So 10, 11, 12, 13, 14, 15 we can consider as a don't care condition. From 10 to 15 is a don't care condition. So we can group here. You can take a group of 4 here. So if you group this particular thing, it's 0, 0, 0, 1, 1, 0, sorry, 1, 1, 1, 0. Here it is 0, 0, 0, 1, 1, 1, 1, 0. And if you observe the row wise, it's Q3, and column wise, if you are observing, it is Q0. Okay. So you got Q3, Q0. Now we need to group this one. So this we can group only 2. So we can write here the common term here. It is Q2. Okay. I think it's Q2 here, and upper portion Q1, Q0. Okay. So T3 you can write like this. T3 is equal to Q2, Q1, Q0 plus Q3, Q0. Okay. So we got an expression for T3. Similarly, you can design for other values also. Okay, now we can design for T2. So if you consider T2, it is equal to 1 again in two cases, 3 and 7. So this is 3 and 7 is here. Okay, these values are don't care conditions. Okay. from 10 to 15 is don't care condition. So we can make a group of 4 here. If it is a group of 4, so T2 can be written as T2 is equal to, here it is Q3, Q2, Q1, Q0. So it is 1, 1. So you can write Q1, Q0. Now we need to design G1 in terms of Q3, Q2, Q1, and Q0. So if you design T1, you can see the alternate values. Okay. So if you indicate the values, it's 1. We need to indicate. Then 3 is here. Then you need to indicate 5. So here it is 5. Then 7. Okay, 7, and finally 9. Here it is 9, and you can see that these values are don't care conditions. So we can make a group like this. So this is 0, 0, 0, 1, 1, 1, 1, 0. Here also 0, 0, 0, 1, 1, 1, 1, 0. In row wise, if you write, there is no common term, but in column wise, you can write T1 is equal to Q. I think I made a mistake. 1, 1, 1, 1, 2, 3, 4, 5. 1, 2, 3, 5. Okay. So T1 you can group like this. So you'll get Q0. Okay. T1 is equal to Q0. I think I made some mistake. I'll try once again. Okay, this is Q3 and Q2, Q1, Q0. Okay, and this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so if you observe this, 1 is there. 1 we need to indicate, 3 we need to indicate, 5, and I think actually this mistake is not in K-map. Here this Q1 is changing from 0 to 0. So this value should be equal to 0. That's a mistake. Okay. So please correct it. It's 0 here, not 1. So then you will get 1, 3, 5. So 1 you are getting 3, 5. Then you need to indicate 7. 7. And these are the don't care condition. Okay. And now we can group only 4 values. Okay. Then it is 0, 0, 0, 1, 1, 1, 1, 0. Here it is 0, 0, 0, 1, 1, 1, 1, 0. Okay. So if you write this, you can write it's Q3 bar, and here it is Q0. Okay. And finally, if you observe, this is for T1, and for T0, if you observe this, all these values are 1, 1, 1, 1, 1, and other values are don't care. So you'll get a K-map like this, and here the values are don't care conditions, and all other values are 1, 1, 1, 1, 1, 1, 1, 1, 1. So T0 is equal to 1. So now we can design one more case, that is this Y. Okay, so Y is equal to 1 for this possibility. uh, which is written by 1 0. Okay, q3 equal to 1 and q0 is equal to 1. So you can put an AND gate and for the reset condition. Okay, now this is a BCD counter circuit, and we already got all these value T0, T1, T2, T3, etc. And this is Q3 bar. Okay, that is written as complement. And now we can see the circuit. Okay, here this is T0 actually. This is T1, T2, T3. In the reverse order also you can draw T3, T2, T1, T0 also you can draw. Uh, here to draw the circuit in a simple way, you are writing T0, T1, T2, T3. Okay, but T3 is MSB actually, T0 is the LSB. Now you can also design this Y part to make it clear. So normally there will be a clear signal for this flip-flop. So to make this flip-flop forcefully clear, we need to connect the clear signal values, okay, value to an AND gate. Okay, so AND gate logic is should be implemented by using the Y logic. Okay, in this case, you already identified that is Q3 should be connected and Q1, sorry, Q0. In Q3, Q0 is equal to 1, 1. The Y output is equal to 1, and all flip flops will be clear. And again, it starts from the initial state. Okay, that's all about the BCD count.